There ain't no man can't save me.
All right, ladies and gentlemen, this is Mr. Ezra, and today we're going to be talking about polynomial inequalities and how to solve them. I'm going to go ahead and warn you that this video might be a little bit longer than the last few videos on characteristics of polynomial functions, so make sure you kind of set aside a chunk of time, 20 or 30 minutes, to at least to get through this lesson. But this is the last lesson in Unit 3A, and that's kind of exciting. All right, so before we begin inequalities, we need to go back in time a little bit and review how to factor and solve equations. So what I'd like for you to do is pause the video and do your best to solve these four equations. You're going to be using factor by grouping, difference of two squares, factoring quadratics. There are some that have like terms that can be factored out. So or common factors that can be factored out. So pause the video, give these a try, and we'll work through them in just a minute. All right, so hopefully you've had a chance to try a few of these equations and you've had some success. Let's take a look at the answers that I got as I was working through them. So when I looked at number one, the first thing that I noticed is that all three terms have an x, which means there's a common factor there, and I can divide all three of those terms by x, pull that x, divide out, factor out that x to the front, and what's left behind is a quadratic. I then looked at this quadratic and I said, I think I can factor that. X times x is x squared, negative 6 times 3 is negative 18, and the sum of the outside and inside products add to negative 3. So negative 6x plus 3x is negative 3x. So this is factoring. You might still be pretty good at that, but if you need more practice, you'll get it today. All right, well, we use what's called the zero product property to get our three solutions. We say x can equal to 0. X minus 6 equals 0 gives us a solution, or a 0 of 6. And x plus 3 equals 0 gives us a solution of negative 3. If we were to set all three of those equal to 0, those would be the three solutions. For question number 2, I have 1, 2, 3, 4 terms, and up until this point in our class, we haven't learned how to solve this without using factor by grouping. Later in the school year, actually before Christmas even, we're going to learn how to solve these using some other methods. But right now, really, all we can do is factor by grouping. So we want to group the first two terms together and ask what is the common factor there, x squared. Group the second two terms together and ask what is the factor there. Well, you have to factor out the middle sign, negative. And since there's nothing bigger than 1 that is a common factor of both x and 3, you just factor out a negative 1, which means that the x squared goes before x plus 3. When you divide both of those by x squared, x plus 3 is left. When you divide both of the second pair of terms by negative 1, you're left with x minus 3. And since x minus 3 and x minus 3 are now part of the first half and the second half, we can pull it out to the front and set it, factor it out to the front. And what's left behind goes into the other parentheses. So the x squared minus 1 goes into the second parentheses. At this point, you should notice that x squared minus 1 is a difference of 2 squared, DOTS. You factor that by taking the square root of x squared and the square root of 1. So it becomes x plus 1 times x minus 1. So this is quite a bit of review, isn't it, of things that we've already talked about that are kind of coming back as part of this lesson. So the three solutions are going to be 3, negative 1, and positive 1. When you set each part equal to 0, those are the three solutions that you get. In the third example, hopefully you were able to figure this one out. We must remember that when you are solving quadratics, there are many methods that you've learned that you can use. Some of you really like the quadratic formula. You could use that here. Some of you like to factor. You can probably factor this. Some of you like completing the square, and you could do that here, but it would be difficult. I wouldn't recommend it. I chose to factor. Before you factor, everything must be on one side of the equal sign. So I had to subtract 15 to the left and get 2x squared minus 7x minus 15 on one side of the equal sign. Then I had to look at the combinations of what would multiply to give me 2x squared and what would multiply to give me a negative 15. And I kind of looked at all of those combinations and realized that what I needed to use was 2 and 1 and 3 and negative 5. So that my inside and outside together gave me negative 7x. So 2x times negative 5 is negative 10x, plus 3x is negative 7x. It works. So my first times my first gives me 2x squared. My last times my last gives me negative 15. And the outside and inside products added together gives me negative 7x. So it factored fairly easily. Wasn't too bad. I set both of these parentheses, both of these binomials equal to 0, and got negative 3 over 2 and positive 5 as my two solutions. And the final equation that I asked you to look at was 50x squared minus 32 equals 0. There's a few ways to do this. One method that you may have used is the square root method, where you basically get x squared by itself by adding 32 and then dividing by 50, and then you take the square root of both sides. I didn't use that method, but I could have. Instead, I first noticed there was a common factor of 2. 2 goes into 50 and 32 evenly, so I divided 2 out front. When I did that, notice that I got 25 x squared, which is a perfect square, minus 16, and 16 is also a perfect square. So perfect square minus perfect square, difference of two squares. I'm able to factor that very quickly with that pattern of the square root of the first part plus the square root of the second part, and the square root of the first part minus the square root of the second part. So 5x plus 4 times 5x minus 4. Now, when I use the zero product property here, the 2 doesn't count because it does not have a variable attached. So it doesn't give me a solution. You have to have a variable in that part of it for it to work. But 5x plus 4 and 5x minus 4 give me two solutions of negative 4/5 and positive 4/5. And this excuse me, this matches up with what we started with, which was a quadratic, and quadratic should have two solutions of some type. All right, so I'm trying to quickly get through several examples of equations, because the first step to solving a quadratic inequality is solving the equation that you're given. So here are the steps for how to solve polynomial inequalities. First, place the inequality in standard form. You notice that's where you put everything on one side of the equal sign in descending order based on the exponent. Second, factor the polynomial completely. Get every factor to a linear factor so that you can work with that and solve for that. Number 3, find the zeros of the polynomial, and that's going to be used to sketch a graph that uses the end behavior for your zeros. And this graph is not going to have to be perfect, but it needs to go through the zeros in the appropriate way, and it needs to have the appropriate end behavior. Otherwise, this method is not going to work. All right. Now, don't forget that when you get a double root or a double zero, that means that it bounces off of the x-axis, and that's still important. We still have to remember that. The fourth step is to highlight the portion of the graph that makes the inequality true. And I don't know if you can read this writing. It's in yellow, which makes it hard to see. It says greater than means above the x-axis, and less than means below the x-axis. And with this method, by looking at the sketch, we'll be able to see what parts of the function are above the x-axis and what parts of the function are below the x-axis. And our final answer needs to be in what we call interval notation. Interval notation. So let's look at some examples of solving polynomial inequalities. You'll notice with these that I've kind of go ahead and started working some of them so that it would be a little bit quicker, but I'm still going to kind of talk through the steps of what to do. So the first thing that we do is we're starting with a quadratic inequality right here. Remember, it needs to be in standard form, so we're going to add 12 to the left, and then we're going to factor. We're going to factor x squared plus 7x plus 12. Well, first we get x times x, and then we need something that multiplies to give us 12, but adds to give us 7. And some of you are like, oh yeah, 3 and 4 is what would work there. These are called factors, x plus 3 and x plus 4. Now we have to get the solutions, which we also call zeros. And that would be -3. -3 plus 3 is 0. That makes that 0. That would work. -4 plus 4 would make this part 0. That would work. So both of these are solutions to the equation, not necessarily the inequality, but the equation version of what we're starting with. We're going to take those equations, we're going to take those solutions, those zeros, and we are going to put them on a graph. Now, this graph does not have to have a lot of detail. It needs to have the two numbers that you're graphing, and they kind of could be about where they would be on the graph. It doesn't have to be perfect, but they need to be in the right order at least. And what we're going to do is use our in behavior and the number of zeros from our quadratic here to sketch the picture that I have. Now this is just a sketch. It's not the perfect graph. Things aren't exactly where they should be, but the things that I know have to be true is that this function has to go through the graph at both -4 and -3. So we're going to use our in behavior from our quadratic here to know what this graph looks like. So it's already, you see that it's already sketched, but if I were sketching it, I would notice that this is a even degreed polynomial. It's a quadratic, which means both ends are in the same direction. I then notice that the leading coefficient is positive, and since it's positive, that means that both arms are going to be up. So I know my end behavior is left up, right up, and it has to go through -4 and -3. So I'm going to start on the top left to go down through, and then back up to get my quadratic graphed. Now, a few things to pay attention to. First, the fact that this is less than or equal to 0 means that if the function goes through the x-axis, that is where it is equal to 0. It's equal to 0 at -4, and the function is equal to 0 at -3. So they need solid filled in dots. They are part of the answer. That out of the way. The second thing is less than 0 means that we are looking for negative part of the graph. Less than 0 means that we want the negative parts of the graph, which is, remember, less than 0, it means below. Below the x-axis is where things are negative. So this part down here is that negative part, and these parts here are equal to, and we put that together to get from -4 to -3. That's the interval where it is either equal to 0 or less than 0. The function is either equal to 0 or less than 0. As an interval, since -4 and -3 are included, they get brackets. So we're going to say from -4 to -3 inside those brackets. So we're going to get from -4 to -3 inside brackets, and this is our solution. All of this work up here is just our way to try to get this one little interval, which is our solution. That's the answer that we want. Let's look at another one. All right, this time everything is on the left side of the inequality sign, but we notice that all three terms have an x. So we are going to have to factor out or divide that x out of all three of those terms and pull it to the front. We now have a quadratic that we can factor. So we would factor that to get x minus 3 times x plus 1. So we've reviewed factoring a little bit today, but you might have to go back to your notes from the earlier in the year if you're still having trouble, because factoring is an important part of this. Now, how many solutions should we have? How many zeros should we have based on the degree of the polynomial? Well, there's a 3 here as our degree, which means there should be at most 3 solutions. Those solutions come from x minus 3, and x plus 1. We set all of them equal to 0 to get the zeros of the polynomial, which are 0, positive 3, and negative 1. We're going to graph all of those zeros on our function. Negative 1, 0, 3. They don't have to be in any kind of perfect location. You need at least those three on there, and that's good enough. Now, in behavior of a cubic, which is an odd degree function, is that the ends are in different directions. And since it's positive, the right side has to be up. That means that the left side has to be down. So as we're sketching this graph, we have to start on the bottom left, go through each of these points by putting curves, and then end on the top right. So we're going to try to sketch that now. We're going to go up, back down, and then back up. Okay. So we still have negative 1 here, still have 0, still have positive 3. Now, this says greater than or equal to. Whenever you have or equal to, that means that you put dots on all of the zeros. They are all included in your answer because this is where the function is equal to 0. Greater than means above. Above 0 are positive numbers. So next we want to know where is the function greater than the x-axis or greater than 0. Well, it starts out being below, and below is negative. That's not what we want. Then right here it goes above. That's positive. We want to shade that. That's good. Then it goes below, negative. We don't want that. And then it goes above forever to the right that way. So we're going to shade forever to the right this way. As we write our interval answer, because these are filled in circles, they are included, they get brackets. Filled in circles get brackets. So we're going to say from negative 1 to 0. We need to include this other interval. So we're going to union it with the U to say or anything greater than 3, which is including the 3 and going to the right forever. Now, remember with interval notation that anytime you put infinity, it always gets a parentheses. So this would be our final answer. This was all that work was to get this interval equate in this answer in interval notation. Try this one on your own. Maybe pause the video, give it a try, and then in a second start the video up when you think you've got it and check your answer. All right, well, we're going to go ahead and start solving this. So let's see if you got what I get. Okay. The first thing that I notice is that there are 4 terms. That means I'm going to factor by grouping. I divide x squared out of the first part, negative 9 out of the second one, always the sign here in the middle. So we essentially group the first 2 together and the second 2 together. And we made sure that we factored out a negative out of the second one. Now 9 goes into 9 and 18, so we also factored out 9. Now the x plus 2 goes into its own parentheses. It's kind of like factored out of both of these parts and it gets its own parentheses, and the leftover bits go into the other parentheses. So x squared minus 9 times x plus 2. X squared minus 9 can be factored further. It's a difference of 2 squares. It gives us x plus 3 times x minus 3 times x plus 2. That means when I'm looking for my zeros, right, my zeros are going to be negative 3, positive 3, and negative 2. On the graph, the negative 3 and the negative 2 are going to be on the left side of 0, and then the positive 3 is on the right side. Remember, we need these 3 numbers in order, but they don't have to look perfect on the graph because we're just getting a sketch so that we can know where is it above and where is it below the x-axis. Well, hopefully you noticed that this was a cubic, 3rd degree, odd degree, which means that the left end is down and the right end is up. And hopefully you noticed that the leading coefficient was positive, which means that the right side is up. So they're in different directions because of the cube, because the degree is odd. And we know that it ends positively because it's a positive leading coefficient. So as we sketch this, we're going to start on the bottom left. We'll use a different color. We're going to go up through, curve back down, curve back up, and get our sketch. Now, Does it have to look exactly like mine? No, but it must start on the bottom left and end on the top right, and it must go through these 3 points, and only those 3 points on the x-axis. Now, hopefully you notice that this was just greater than. And just greater than is not equal to, so we use open circles on this graph. Wherever there is a 0, what we want to say is that these are important parts of the graph, but they are not solutions themselves. They're not going to work for this inequality because it's greater than but not equal to. Now we want to look at the parts of the graph that actually are greater than, and these are the positive parts. This part here is positive. We shade between -3 and 2. This part's negative, it's below. This part is positive. We shade to the right there. So our answer is going to be, using parentheses because the zeros are not included, from -3 to -2, union from 3 to infinity. That will be our answer to this question. We've done a lot, haven't we? Several examples. How are you doing? Feeling all right? You can see that when we study something like factoring or factor by grouping or difference of two squares, it comes back to haunt you if you don't learn it the first time well. We don't get enough practice in. Hopefully you've got enough practice and you're feeling good and you're ready to move on. Well, let's look at a few special cases. Some cases where things don't work out the way that they have up until now. Okay. Now what we're going to do with these special cases is I've kind of already written out most of what I want to talk about. We're just going to mention it. In the directions for how to do this, we mentioned that you have to pay attention to things called bounces. And remember what a bounce means is a bounce happens when you get a double root or a double zero, when the same solution occurs twice. Instead of going through the x-axis, your function bounces off of the x-axis. So in this case, x plus 2 squared, notice the leading coefficient is positive. There are two x's, which means that it's even degreed. Both ends are up. And it only touches at 2. It's a double root. So as we come down, sort of kind of sketching this graph, when it hits 2, it's going to bounce back up. Okay? That's important to get our picture right and to understand how we get our picture. Now we try to interpret our answer. It says greater than 0. At 2, it is an open circle because it is not greater than 0 there. It's equal to 0. We have two positive intervals because both of them are greater than 0. So we are going to shade to this one's positive and this one's positive. So we're going to shade to the left and to the right of 2. But it's important to note that 2 is not a solution. Our solution is everywhere on the x-axis except for 2. X cannot be equal to 2. In interval notation, that means we're going to start at negative infinity and go all the way to 2 and make a pit stop there. And then we're going to union that with the next interval, which starts at 2 and goes forever to the right. And this is our interval way of saying everything but 2. Because of the parentheses on the 2 there, it means that it's not included. Our second special case over here. We're going to use the same example, but we're going to change the inequality. So this time, instead of greater than 0, we have less than 0. Okay, now, so the picture is the same. Let's not talk about that again. But let's talk about where this graph is less than 0. All right. It's equal to 0 at 2. Well, that equal to is not less than, so we can't use that one. Both of the intervals on the left and right are positive, which are greater than 0. And you'll see we have no part of the graph that is below the x-axis, which would be a function that has a part that's less than 0. So there's nowhere for us to shade. We can't shade on the left or the right because those are positive, not negative. We can't shade the 2 itself because it's not included. So how do we write this? Well, there's no solution. There's no answer that works. There's no interval that works, nowhere. We sometimes call this in math an empty set, which is a fancy way of saying no solution. It means that the set of solutions is empty. There's nothing there. Didn't work. All right, our next example, we're going to change the inequality again, and this time it's going to be greater than or equal to. Well, greater than or equal to means that we do include the 0, because equal to 0 is where it crosses the x-axis. Greater than 0 is anywhere where it is positive, and it's positive on both sides. So we're going to shade the left side because it's included, and the right side, which is included. So it looks like everything on here is included. The 0 is included, the left side and right side of it are included, so everywhere is included. Well, our one way that we tend to write this answer is the symbol for all real numbers, or the words all real numbers, but in interval notation it would be from negative infinity to positive infinity. Everything is included as part of the solution. No matter what x you plug in here, they're all going to be true. Again, the same graph, except this time it's less than or equal to 0. So here we have a double root again. Both ends are up, and we want to know where is this function less than or equal to 0. Well, this function that we've drawn is not less than 0 anywhere, because there's nowhere that it goes below the x-axis. But it is equal to 0 right here. Where it crosses the x-axis is where the function is equal to 0. So it's equal to 0 at 2, and that's part of this solution. So it is only at one place that this would be a true statement, that only one solution is going to make this a true statement. And that's where x is equal to 2. In an interval, it's not really an interval, but we can in a brackets put just the number 2, which means that we're starting at 2 and ending at 2, and we're only including 2. So that's the way that you can write it. So these special cases we need to take into account as we get to some of the more difficult problems where there are bounces. We got to think about those bounces and what they mean in our final answer. For example, we have to this solve x minus 1 squared times x minus 11 greater than equal to 0. When x minus 1 is squared, it means there's 2 zeros. Because it's squared, positive 1 is a 0 2 times. 11 is a 0 1 time. So we've got the 1, which is what we call a double root or a double 0, and the 11, which is a regular root. Got to remember when we're graphing this that this is going to be a bounce. This one's just going to go through. Okay. Well, I'm going to go ahead and fill these in with closed circles. Why am I using closed circles? Because it says greater than or equal to, and the or equal to means that these 2 points are included. I'm then going to try to sketch this now. It's got 3 solutions, which means that the degree is odd. When the degree is odd, if the leading coefficient, which in this case we don't have a leading coefficient, but if we multiplied everything together, it would be a positive number. We know that it's going to end up, and that the ends are in different directions. So the left side's down, the right side is up. All right, we're going to start to the bottom left. It's going to bounce off that double root and then go back up through this one. Okay. So as we're kind of separating this out, it's less than over here. This is included. It's less than here because it's still below, and then greater than here. We're looking for greater than or equal to. So what we want is this part here where it's above the x-axis. We also want these 2 zeros because it says or equal to 0. We don't want anything that's less than. We only want greater than or equal to. To write that in an interval, we're going to say that 1 is included and that anything greater than 11 is also included. Last one. I told you that this video was going to be rather long to set aside some time. I'm really sorry about that. but it had to be a long video, or I had to have split it. So I just decided to power through, give you one kind of longish video for this one. We have 4 terms with one of them on the right side of the inequality. So we subtract 64 first, and that step is kind of missing here. So I'm going to add that in. That's kind of the first step, is to get everything on the same side of the equal sign. Then we're going to divide x squared out of the first 2 terms, leaving us behind x plus 4. We're going to divide negative 16 out of the second 2 terms, giving us x plus 4. The x plus 4 comes into one parentheses, and the x squared minus 16 goes into another. X squared minus 16 is a difference of 2 squares. We can factor it further as x plus 4 times x minus 4. Once we have solved this, once we've gotten through that, we have to list out our solutions, or our zeros, okay? So the zeros are negative 4, positive 4, and negative 4 again. So what does that mean about negative 4? Well, at negative 4, we have a double root. So we want to make sure that we kind of remember that as we begin to sketch our picture. 4 is just a single root, regular root. This is a cubic. Sides are in different directions. Positive leading coefficient means the right side is up. So we're going to start on the bottom left. We're going to bounce here, go up, bounce, and then go back up again. Now, less than or equal to means that the 2 points are included. They're important. They're equal to 0 there at negative 4 and there at negative 2. The less than means that we want the negative intervals, the ones that are below the x-axis. Well, there's a negative one on the left, a negative one in the middle, but the one on the right is positive. So we want this guy on the left, we want this curve down here, which means that we're looking at all of the x values, including negative 4 and 4, and everything kind of between them and to the left of them. So while this looked like it might be more than one interval, our answer is actually going to be from negative infinity to positive 4. Since everything from negative infinity on the left to 4 is included, we are going to make sure that we just start at negative infinity, include everything, and then we stop at 4 and say 4 is also included, so it gets a bracket. And that is our final solution. You've got lots of practice for this to work on. They can be a little bit challenging at times. You've got to review factoring and solving equations before you can get your sketch. But by the time you get through the other end, you're going to be much stronger with the quadratics, with factoring, the different types of factoring, with sketching graphs, and we'll be ready to start preparing for our next test. Thanks for paying attention for so long today, and I'll see you in class.